Yay. Okay, so just to finish off what we were doing last week, right? The next thing to talk about is vapor pressure. Remember, we were talking about evaporation, and evaporation is basically phase changing from liquid phase to gas phase, right? And then to do that, what happens is you put in a lot of energy, right? And when you put in that energy, kinetic energy, what do? You spread the molecules apart. When they're apart far enough, they become a gas, right? Well, what a vapor pressure is the pressure of the vapor of that liquid that's above the liquid, right? So I had this glass of water here, right, and there was water in it, and then at the top there's water vapor at the top of it as well, right? And the pressure of that water vapor at the top is what's keeping the water from the bottom from evaporating. Does that make sense? Right? And so what can I do to overcome that pressure? I can heat it up. I can heat up the water, right? And then the pressure of the water, the liquid water, that will be higher, and then it will overcome the vapor pressure that's above the water, so that you can evaporate the water that's inside the bottom of the cup, right? The liquid water. So what you see here then, excuse me, what you see here then is the fact that even without, and I've talked about this so many times before because I spill things all the time, and I keep on telling you about Gibbs free energy, right? Even though you have a cup of water here and you don't heat it up, eventually it dries, right? Eventually the water will evaporate. And that's because some of the molecules in the water, right, already have enough kinetic energy to actually just evaporate. Otherwise, your stuff would be wet all the time, right? Your stuff would be wet all the time if you spilled yourself on yourself, right? And so what you see here, right, is this line is the kinetic energy in the molecule that is required for it to escape the liquid phase and become gas, right? And this blue line here, right, shows a vast majority of the molecules right here at lower temperature and this low kinetic energy, right, needed to become let me say that again. The vast majority of the molecules right here, so mole fraction, right, is just a fraction of the molecules, or the fraction of 100%. If you thought about it like the cup of water right here, is all H2O, right? And so 100% of that water is H2O, right? And so you can say then the fraction is that fraction of H2O molecules. And so up here is 100%, down here is 0%, right? And so you need higher temperature here to get some of those molecules to escape, and you need lower temperatures here. These lower temperatures are the ones that already have enough kinetic energy to escape, right? So really the only thing you need to know about this is the two statements I put right here. At any temperature, some liquids have enough energy to escape the surface and become a gas, right? And then as the temperature rises, the fraction of molecules that have enough energy to break free increases. Those are the two statements you need to know, okay? You don't even have to remember this graph. This graph really just describes these two statements. But these are the two important statements I might ask you about on the next exam, right? True or false, or which is the most important, or whatever, right? Everybody got that? Okay, so a little bit more about vapor pressure here, okay? As more molecules escape the liquid, the pressure they exert increases, and then the liquid and the vapor each reach a state of dynamic equilibrium, where the liquid molecules evaporate and the vapor molecules condense at the same rate. So what we're saying here, right, is that I have here some ethanol that's liquid, right, the same kind that you drink, right? And then what can happen is that I can make right now, there's a little stopcock right here, and that stopcock keeps the ethanol inside of the burette up here, right? I know you guys know what a burette is, right? You know, you used it in Gen Chem to do titrations. Remember that? So this little burette funnel thing here, it actually has a lid on it. So what happens is you can open this up, and then the liquid will start coming down here. But before it comes down here, the flask is actually in vacuum, right? The flask at the bottom is actually in vacuum, right? So literally what will happen is that when you open the stopcock, since there's a vacuum, it's the same thing that happens with a syringe. It sucks the ethanol into the bottom of the flask, right? And then since this is a closed system, and you just suck the ethanol into the bottom of the flask, it starts to evaporate, right? Because when you have things at a lower temperature, sorry, lower pressure, they'll evaporate at a lower temperature. Okay. So after that starts, it'll get to a point where the amount of the rate at which the rate at which the liquid becomes vapor is now equal to the rate that the vapor becomes a liquid, and that's called the dynamic equilibrium. Okay, does that make sense? That's called the dynamic equilibrium. Okay, and this happens in this closed system here, right? And again, this is the vapor pressure up here. That's so remember that the vapor pressure P is that pressure of the vapor of ethanol at the top. And you see molecules of ethanol, right, going in and out of liquid phase, right? So you have some in the gas phase up here, some in the liquid phase, and they're going back and forth. And when they go back and forth at the same rate, that's called dynamic equilibrium. Okay? And it says that down here too, right? Molecules leave and enter liquid at equal rates. Pressure reaches a steady state value, which is the dynamic equilibrium. Okay? So what I want you to get out of this is this next slide here, okay? Where when you're at dynamic equilibrium, right? The rate of evaporation of that's not ethanol, that's like, what is that? 1, 2, 3, 4, 5, 6. I think that may be hexane. I'm not sure what that molecule is. It's a little bit too crunched up for me to count up the molecules. But if it is hexane, whatever, the rate of, maybe it says it up here. Does it say it up here? Of course it doesn't. Anyway, so when you have the rate of evaporation equals the rate of condensation, which means the rate of the molecules becoming a gas and the rate of the molecules gas becoming liquid are the same, we have dynamic equilibrium, like they said in the previous slide. So the thing is, though, that right when the volume is increased, right, inside of a closed system, right, the pressure falls. The pressure inside the vessel falls, right, and then when that happens, it's a lot easier to vaporize the hexane. Let's say it's hexane. Okay, it's easier to vaporize. So in this case, the rate of evaporation is greater than the rate of condensation, right? So when you increase the volume in a closed system, so think of that like it's a syringe plunger right there, and there's nothing at the bottom right there to let anything out. What happens inside? The pressure decreases. It turns into a vacuum, right? And when it turns into a vacuum, the pressure that is above the liquid is no longer as strong, right? And so more of the liquid can become a gas, okay? Regardless of what the temperature is. If the volume is decreased, the pressure rises, and then more gases become the more gases become liquid, right? So literally, you're pressing down with the plunger now. There's nowhere for the gas to escape, and so the pressure there's not as much room for the vapor pressure anymore, right? And so most of it becomes liquid, right? I'm trying to think of a. Oh, this is a really good, easy way to do this. Everybody ever heard of a pressure cooker? Why do you think you can make like a pot roast in a pressure cooker in like 30 minutes, right? Instead of having a pot roast there all day. And the reason why is because you change the pressure inside of a pressure cooker, right? And it makes things hotter faster. Does that make sense? So you don't have to have it cook, and it breaks down things faster too. So that's I think I'm pretty sure Chick-fil-A does their chicken in pressure cooker deep fryers, but I know for sure that Kentucky Fried Chicken uses pressure fryer deep fryers, right? That's why Kentucky Fried Chicken has this like very specific flavor to their chicken. It's not just because they're seven secret ingredients or whatever herbs and spices they put in there. It's also because of the way they cook their chicken. So you can also do this. Has anybody ever heard of an autoclave before? So hospitals use autoclaves to sterilize things. And the reason why they use autoclaves to sterilize things instead of just using ethanol or using boiling water is because water boils at 100 degrees, right? And the problem with water boiling at 100 degrees is there are some extremophile bacteria that can survive 100 degrees. For example, the bacteria Thermus aquaticus, which is the one that they use for doing PCR, polymerase chain reaction, where you're doing like DNA profiling for forensic sciences, or you're doing like genetic manipulation, like with CRISPR. All those things require PCR, and they use an enzyme from a bacteria called Thermus aquaticus, and they live in the hot springs of Yellowstone, where the water gets regularly above 100 degrees and becomes vapor, right? And so, if you were just to boil water, right, and kill the germs, you're not actually killing Thermus aquaticus, for example. Does that make sense? Right? Because they can survive that. And that's why when you look at the back of things like hand sanitizer bottles, right, or use boiling water, if you have a shark vacuum, a shark mop, they always say sanitize your floors. Well, they can't say sterilize your floors for a reason. And the reason why is because when you're sanitizing, you're only killing 99.99% of bacteria, right? That's called sanitation, okay? And that's because boiling water can only kill so much, okay? Whereas if you use pressure like this right here, right? If you use pressure, you can actually make it where the boiling point of water is a lot higher now. It's going to be like 121 degrees Celsius instead of 100 degrees Celsius. And now you can kill Thermus aquaticus, right? And so when you can kill Thermus aquaticus and all these other viruses that can survive hot water, boiling water, right? That's called sterilization, and that means killing 99.9999% of all bacteria. So there's a big distinction between having sanitation, right, which is killing 99.99% of bacteria, and then sterilization, which is killing 99.9999, which is four nines after the decimal point, right? And the way they accomplish this is through this. Since you put pressure on it, and I think it's 15 psi they do in an autoclave. They put 15 psi down here and they push it down with the pressure. And when they do that, it makes it so that the liquid here now has a higher boiling point. Okay, so increasing the pressure gives you a higher boiling point, and now you can do things like kill bacteria at 99.999%, and that's sterilization. Right? So, like even in your dishwasher, now I have a sanitation mode on my dishwasher. That's because you can get up to boiling water in the dishwasher, but you can't get up to 115 degrees boiling water. I mean, sorry, 121 degrees boiling water, right? So, long story short, when they are evaporating and condensing at an equal rate inside this closed system, that's called the dynamic equilibrium. When you increase the volume, you get a decrease in pressure, right? And then you also get a decrease in the boiling point, right? Things boil faster. And then up here on this one, volume is decreased, right? And now the boiling point is increased, right? Because the pressure is increased. Make sense? Okay. Good stuff, good stuff. Any questions? Okay, so there's this thing called the supercritical fluid, right? Gases liquefy when pressure is applied, which I just said that, right? You have water vapor, and you push down on it really hard, and it turns into liquid water even without any cooling, right? And then the temperature beyond which a gas cannot be compressed is called the critical temperature. The pressure needed to compress the liquid is called the critical temperature. Critical temperature is called the critical pressure, right? And so there's a state that's beyond both of these that's called the supercritical fluid. So here we have and did I talk about this last week where we were talking about making dry ice, right? You can take dry ice, or you can take a cylinder of CO2, which is just gaseous CO2, and put it into a really strong compartment and press it down really hard, right? And then we'll make dry ice. We used to have that machine at my old school. It was a lot of fun, right? So here's liquid CO2, right? And here's gaseous here's liquid CO2 and here's gaseous CO2, right? Inside this closed system. And then you can start increasing the temperature, right? This closed system doesn't have any pressure changing. You can't manually change the pressure, but you can change the pressure inside the system by heating things up. Because when you heat up the CO2, more of this liquid CO2 becomes gas, and now the pressure up here is much stronger, right? You keep on heating it up, and then eventually it gets to a point where this liquid is like it's like everywhere now, right, inside the small little system. And then at some point, right, you can't go any further. At some point, can't go any further. The pressure is so high inside that the liquid can't become a gas anymore, right? And vice versa. And now that's called a supercritical fluid, right? You've reached the point of a supercritical fluid. Okay, it's good stuff. So, okay, so here's a little chart called the Clausius-Clapeyron equation, right? And I'm not going to really make you do anything with this until next test, right? So we won't focus on this too much today. I don't want to work any problems because if I work problems, it'll take a long time, and so we can do it later so that we have time to review for the exam. But just as a conceptual thing, the boiling point of a liquid is the temperature at which the vapor phase equals the atmospheric pressure, right? So again, with my cup of water here. Um, if I'm boiling my cup of water, right, and uh, the boiling point, once it reaches the boiling point, right, that pressure there is equal to the vapor pressure, right, of the pressure up here is equal to the atmospheric pressure, and that's when things can start evaporating, which I said that before already, right? And then the normal boiling point is pressure at 760 torr, which 760 torr is just atmosphere here, right? Like this is what we are sitting at, 760 torr right now, which I believe is also the same thing as 760 milligrams mercury's millimeters, right? But it's also the same thing as 1 ATM, 1 atmosphere, okay? And so when we look at this chart up here, I will definitely ask you questions about this chart on the next exam, right? We've got temperature on the z-axis, the z-axis, this temperature on the x-axis, and we have vapor pressure on the uh, y-axis, right? And let's look at something that we know pretty well right here. This blue line right here is water, right? And notice as the temperature increases, right, the vapor pressure increases until the vapor pressure is the same as it is in the atmosphere, which is 760. So 760 vapor pressure for water, right, is at 100 degrees Celsius. And guess what? The boiling point of water is what? 100 degrees Celsius. Does that make sense? So the boiling point is literally where the vapor pressure of the liquid equals the pressure of the atmosphere. Okay. So here's another liquid that's dear to my heart: ethyl alcohol or ethanol. Had some this weekend. It was pretty good. It's probably why I didn't get any work done this weekend. Anyway, so we start here again with the vapor pressure being at 0, and then as we heat it up, for ethanol though, ethanol's boiling point is actually 78.3 degrees Celsius, right? Where it becomes the same vapor pressure as the atmosphere, okay? This is actually the reason why you can distill alcohol from water, right? If you didn't know, when you make beer or you make vodka, I used to make vodka all the time with by throwing yeast in with some bacon, and it was a good time making bacon vodka. But at the end there, you want to get all that yeast out of there. You want to drink any yeast with your alcohol. So how do you do it? Well, you do this thing called distillation, right? And distillation separates liquids based on their boiling point. And so what will happen is that when you put the pot of like what they call a mash, right? With the yeast and all that stuff, you gave the yeast to actually make alcohol in the water. You put it onto a hot plate or a Bunsen burner or whatever, and you heat it up to 100 to 78 degrees. And when you heat it up to 78 degrees, all the ethanol will evaporate, leaving the water behind, and then you can collect the ethanol in another pot on the other side. And that's how they distill ethanol. Okay, so this is something that's pretty cool that I when I learned this, I was like, wow, that blew my mind. The problem with having this kind of graph, though, is that you have to do like estimations, right? These are all exponential graphs, and so when you're like, I can't really tell where the y-axis intercept is. If I want to draw a line, it's hard to predict what's going to happen right here, right, with these curved lines. But when you have a straight line, right, you can always use the slope to figure out what each point is. And so Clausius and Clapeyron came up with this equation where they took 1 over the temperature, right, and they took 1 over the vapor pressure, which is what this is right here, and it turned these exponential equations of these lines into a straight line. Now you have a very clear y-intercept, you have a very clear slope, and you can start predicting things, right? So if you didn't know that, if you have a chart, you have a graph that has an exponential relationship, and you're trying to figure out the kind of trend or predict other numbers on it too, right? And I'm going to ask you to do this later on. If you're trying to predict, different temperatures or different pressures, it's hard to do this because there's not a clear y equals mx plus b graph for an exponential relationship, right? But if you were to take the vapor pressure and if you took the 1 divided by the vapor pressure and then 1 divided by the temperature, it becomes a very straight line, and then you can go through and calculate what you want to do to predict it, right? We won't spend too much time on that today, but we will definitely work some of these on Wednesday, okay? And that's the equation right there to figure it out. So, this is your first question for today. I even gave you the little graph here to try to predict it, but notice you're kind of guessing here because it's not a straight line graph, okay? So the question here is, estimate the boiling point of water if the external temperature, estimate the boiling point of water at an external temperature of 200 torr. Well, that's weird. They changed the colors. The water was blue before. Maybe I did that. I don't remember. Go ahead and do that. And I want you to see the fact that you actually are just predicting and guesstimating here. But next Wednesday, when we talk about the Clausius-Clapeyron equation, you'll see that we can get an exact number. What the heck? What? If every single time I log onto this computer, it acts like it's the first time I've ever logged onto this computer. Come on, almost there. Okay, there we go. Oh my God. I'm glad my username is short. Sorry, I gotta put in my code. 562-297. Don't show this again. Stay signed in. Well, it never worked, so I don't know why I did it. And this one was polarization. Boiling point of water. There it is. Wow, everybody's in already. Wait a second, that's not right. That's the wrong one. Ah, that's it, vapor pressure. There we go. Okay, so let's see what everybody said. All right, so most of you said A, and 2 of you said C. I've already forgotten what the answer choices were. Yes, the correct answer is in fact A, right? Because, let me switch over back here. When you have 200 right there, right? And you go over to the line for the vapor pressure of water, it's around 66 degrees. right? Okay. But the thing about it is that you're like guessing. You're just guessing, right? You're really just guessing. But on Wednesday, I'll show you how to use the Clausius-Kepleron equation to actually figure out the exact number. Okay? But we won't go through that today because that's just going to blow your minds before the exam. We don't want that to happen, right? Okay, so these are the last three slides right here. Okay? They're all going to be pretty much about the same thing. Okay? So there's these things called phase diagrams. And in a phase diagram, you can see, right, where certain substances will be at certain phases, right? So on temperature on the x-axis, pressure on the y-axis, right? You can see that here when it's a solid is over here, okay? This is when it's a solid. And you see how everything's stacked together very nicely. And over here, it's a liquid, a little bit further apart, but still pretty close together over a liquid. And then over here, here's a gas at the very bottom, right? And things are super far apart, okay? So here you can see the line, and this line here shows the increasing pressure and increasing temperature, right? In both directions, okay? And remember, this is a supercritical fluid and critical point we were talking about before. Pin that for now. The thing I want you to notice is this, okay? Notice at a certain temperature here or a certain pressure here, you can do sublimation, right? Where sublimation goes from solid to gas, or deposition goes from gas to solid, right? So at this point right here, right, you can go sublimation or deposition. So you have a point here where you have a pressure that's right here and a temperature that's right here, okay? Then you can do sublimation. Turns out that CO2 is there, right? That's why it can go from solid CO2 to gaseous CO2. You get to this point up here called the triple point, and that's where it diverges so that you can have condensation and evaporation right here between liquid and gas, and then melting and freezing between liquid and solid, right? So normal phase changes are up here on the red and blue, right? But when you're at the low temperatures and low pressures, you can do what? Deposition and sublimation. Okay, that's important right there. Okay, so the phase diagram shows the state of matter under conditions of temperatures and pressure. It also shows the state of the it also shows changes of state in the triple point and the critical point, right? So let's take a look at the phase diagram for water real quick. Again, the most important things you need to know are going to be over here, right? Well, so here's water, and notice, right, there's the triple point of water, right? But we very rarely ever get this low in temperatures, and we very rarely ever get this low in pressures. So most of the time you're up here, where your 0 degrees is right there, and water evaporates, right? Gas, liquid, and solid. But notice this temperature right here. This temperature, remember when we go from liquid to gas, right? Oh, sorry, liquid, solid to liquid right here, that's called sublimation, right? And the deposition between gas and solid right here. Notice this temperature. That temperature is around 20 degrees, minus 20 degrees Celsius, right? What's the temperature of your freezer right now? It's minus 25 degrees Celsius, actually. It's the temperature of your freezer. If it's not that, then you've got a broken freezer, right? And notice that since this line right here to go between gas and solid, the sublimation line, right, is right there where your freezer should be. What happens to things you put in the freezer? Huh? They freeze, but what else happens? We talked about this last week. Your freezer is like negative 25 degrees Celsius, right? And this line right here to go between gas and solid, it stops here right at the 20-degree mark, the negative 20-degree mark. This is what causes freezer burn, right? When you have like a steak or vegetables or whatever that have liquid water in them and you put them in the freezer, right? The freezer gets just to the temperature. So you notice sometimes you don't get freezer burn, but sometimes you do get freezer burn. And the reason why that is because the sublimation line right here is right there at the same temperature of your freezer, right? And that's why liquid from your food will go straight to gas, not even go into the liquid phase, right? It will freeze and then go straight to gas. Yes, because of sublimation, but specifically in water, because the sublimation line is at the temperature of your freezer, right? Okay. Here's carbon dioxide. Same thing I was talking about before, right? There, look at this, right? Right? Solid carbon dioxide, right, can go from solid to gas, right? Right here at normal pressure too. See, here's normal pressure, 1 atm, and we have normal pressure. What is the line? It's a line. Is a line the sublimation line, or is it the line between liquid and solid and liquid and gas? It's a sublimation line, right? And that's why solid CO2 can go straight to being a gas. And it's because at 1 atm, which is our pressure, our atmospheric pressure, it hits the line of sublimation, right? Contrast that to water, right? Where at 1 atm, right, where are we at right here? We hit the line between normal phase change, right? Condensation, evaporation, and melting and freezing. Notice that? Do you see the difference there? Do you see how on carbon dioxide at 1 atm we hit the line of sublimation, right? But then on water we hit the line of evaporation and melting. Make sense? At 1 atm. Okay? And then this is the last slide and the last question. Go ahead and try it out. And then we'll have 30 minutes to review. And I don't even know the answer to this question because I haven't even read it. I should probably read it. Excuse me. Forms. Where is this question at? That's what happens when I have so many. Ah, triple point. That's it. So far, only 5 people have answered. Take your time. Take your time. We're still at 6. 7. 8. We need 3 more. 9. I'm expecting this to be kind of all over the place here, but that's okay. I know you're focused on your exam. 10. One more person. One more personnel. Okay, there we go. Okay, so the vast majority of you put C as your answer. Nothing. The solid will remain a solid. I'll show you real quick. Right? So most of you put C, a solid will remain a solid, right? I won't make you discuss this. I'll just go ahead and work this out for you real quick. Okay? So the question says, right, that you have a triple point. And remember what a triple point is. The triple point is that thing right there, right? That little point right there. Okay. So let's draw this out. We have, oops, sorry. Gotta activate my pen. So let's draw that out, right? And then the line somewhere, if you look at the other graph, it starts like down here somewhere, and then splits off like that, right? Okay. And it's telling you, the question is telling you that you have a triple point that is at negative 25 degrees Celsius. So temp is at the bottom. Okay. Pressure is over here. For how to spell pressure. There we go. Pressure is there, right? And it's telling you that the point. What's going on here? The point here, right? Dang it! What in the heck? All right, we'll just do it on the board. All right, let's try this on the board again. Okay, so we have our thing that looks like that, and then temp is at the bottom, and then we have our pressure over here, right? And then we have this little line that goes like this, right? And this right here is the triple point, right? And so here's solid, okay? Here's liquid, thank you. I lost my train of thought. And then here's gas, okay? And then it says that the triple point is at negative 24 degrees, so we'll just draw a line on there, negative 24 degrees, 0.5 Celsius, okay? And then this right here is at 225. So that's pretty low pressure because normal pressure is 760, right? And so it's saying that you're going to, what will most likely happen to a solid sample substance that is warmed up from negative 35, right, to 0, okay? So negative 35 is over here, right? Negative 35 is over here, and 0 is all over here, right? So you're warming up, you're going this direction. So already your solid is going to be, right, either liquid or gas. Does that make sense? Right? Because you're already all the way over here. And then at 220, which is down here, right, like that. Does that make sense? And what was this line right here below the triple point? That was a sublimation line, wasn't it? So your solid is going to change from solid to gas because this is sublimation. I think so. That's what it was. I can't remember now because I can't even access it anymore. Let me try to get it back. Oh, there it goes. There we go. So if I ask you a question like this, right? And I will ask you a question like this, right? Yeah, the answer would be B. The solid sublimes into a gas because it's still below the triple point. Make sense? All right, that's it for today's lecture.